All right, welcome everybody. My name is Wendy Ferry, and this is our first presentation for this session. I want to let you know that Tien is going to take a few breaks during his presentation, two different breaks where he will answer some questions, and then we'll have some time for questions and answers at the end. Let me see if I can share my screen here. All right. So let me go back a slide here. We're at the 2021 Virtual Summit. And we'd like to start the session by taking a moment to honor the land and thank its original stewards. In the Seattle area, we are on the ancestral lands of the Duwamish and Salish Sea tribes. If you're attending from another area, we encourage you to learn on whose traditional lands you work and live. We want to remind everyone to exercise respect for other attendees. Please help us foster an inclusive environment during our sessions. If you are someone that normally speaks first, please check yourself and leave space for those, particularly BIPOC colleagues, who may have been socialized to hold back. If you normally hold back, consider taking up some space here. I'd like to take a quick minute to thank our sponsors, especially presentation sponsors, Dunn Lumber, Small Planet Supply, and Tacoma Public Utilities, and our sustaining sponsors, King County Green Tools and Pharos Creative. This event is truly not possible without the support of all of our sponsors, and we are truly grateful for all of their support. And with that, I will stop sharing. Maybe. Okay. And today, during this presentation, we are going to be hearing from Peng, and he's going to talk about concrete carbon solutions. And with that, I will turn the presentation over to him, and I'll turn myself off and let Tien have the floor. Thanks, Tien.
Thank you, Wendy. Thanks everyone who showed up for the presentation. Let's see, I will start by saying I am a longtime resident here in the Pacific Northwest, been in Seattle for 20 some odd years. I worked, in fact, for Quadrant Corporation, if anybody had been around that back then, where we did a lot of market rate affordable housing projects in the region. I was in the Washington State Building Code Council, where we did a lot of big steps for reducing the energy consumption of our built environment. And currently I work for the National Ready Mix Concrete Association. And the association is made of members of the concrete producers. More than 50% of the production of ready-mix concrete in the United States. And I do education, training, as well as advocacy work. So hopefully that gives a little background. Let's see if I can start my, oh, good. So yes, concrete, as we all know, is the literal foundation of our built environment. We use it for infrastructure, bridges, roads, foundation systems, of course, wastewater treatment plants, and so on. And so there's really no future right now without, at least immediate future, without the use of the material. Um, but of course, there is a looming deadline. We have all heard about the Paris Accords, climate accords, that is trying to reduce our carbon emissions into the atmosphere. And the deadline 2050, 2030, you've seen many of those challenges. We know that building materials and construction is essentially 11% of the global carbon emissions. And we want to reduce that. If you look at the bar chart on the left, you'll see that when you first build a building, say in 2020, it is all what's called embodied carbon. That's the yellow. And as you operate the building and use the building, you start using energy. And that operational carbon starts to grow while the embodied carbon, of course, stays the same, more or less. There's some maintenance involved that changes the embodied carbon, but by 2050, you'll see that essentially the operational and the embodied carbon are equal. Really, everybody has been working on operational carbon, that leaves at that is the reduction of energy use, heating and cooling for our buildings, for a long time. We all know how to do it, and there are many good examples of net zero buildings, in fact. Um, so the drive, the goal is to reduce the greenhouse gas emissions of some of our materials in addition to that operational. From a Washington state standpoint, we know this is the 2018 is the figure that I have most recently, um, that the industrial processes, agriculture, and waste, I think, yeah, waste management is that other portion that is the 15.4% that you see. Again, we are all working on in residential and commercial and electrical use of our built environment. Transportation remains the largest. And in Washington State, the legislature has signed a new commitment, a climate commitment, May of this year, that is to reduce the future greenhouse gas emissions as measured against 1990 levels. And right now, we have a big task ahead of us. And um, we also see that the legislature, beyond the governor's climate ambition, has also signed recently the capital budgets. There's a proviso that basically 7041 basically says the Department of Enterprise Services will recommend how to apply carbon reduction strategies to state-funded buildings. And so I'm actually a part of that work group. There is a number of other bills around the country, as well as regulation and legislation, many of them called Buy Clean Acts that you might have heard of, which seeks to reduce the embodied carbon content emissions of our construction materials. And so we know from research that 50%, more than 50% of the upfront embodied carbon comes from the structure and basically the superstructure and substructure of buildings. So hospitals, offices, schools, all basically say that if we want to reduce the embodied carbon, it comes from the structure. So now currently there is a green material narrative that you hear addressed to the specifiers, the architects and engineers out there, that says, each material has their competing against each other, but each material also has their strengths. recycled content for steel. Steel is, 90 something percent recycled content. For concrete, it's always a local material, right? You're not going to be shipping concrete from, upstate New York. And then wood, of course, is promoting their carbon sequestering abilities. But really, what we've learned in the past, I say, 5 to 10 years, that these type of this language of single attributes are such as transportation distance, recycled content, renewable, what materials, renewable bamboo, all of this is essentially a proxy for what we think is true sustainability. The true sustainable measure looks at all of these things at the same time and understands that really everything we do has a trade-off, right? You using your phone, you driving a car, taking paper towels, all of that is has trade-offs one way or another. So concrete itself is actually a low impact material. If you look at this research study, the amount of energy used to produce the embodied carbon of each material is showing that concrete is in fact a pretty low carbon material. But it's a durable material, obviously, and it's inexpensive, and so that's why it's used so much. But these numbers are on a per weight basis, which is not really meaningful because you're not using the same weight of materials. And so, again, the reason why you've often heard that concrete and steel is responsible for 8% of the global greenhouse gas emissions is because the world used so much of it, right? The world is using this, the developing nations are using concrete to build their infrastructure for progress. And so the amount that's being used is essentially driving that number. So I don't, I'm sure the audience here knows the difference between cement and concrete. But just to recap, cement is that more or less 10% of the ingredient of concrete, which includes fine and coarse aggregate water, air, and some admixtures or some other materials to meet a particular performance. And so cement, as it turns out, is essentially 70 to 80% of the carbon footprint of concrete. And so the drive to reduce the carbon footprint of cement is the primary goal for the industry. But remember, if you look at how much, this is just for expectation setting for us in here in Washington, look at how much cement is being used. This is in tons in the other countries, the developing nations, China, India, Vietnam, compared to the United States. So just to set the expectations, what can we do here in Washington is essentially demonstrate our leadership position. The effects of what we do here is a pretty minuscule compared to what we can do in China. However, having said that, the Global Cement and Concrete Association have already committed to a reduction of net zero by 2050 cement, 20 net zero cement, and that includes the major companies in China. So we are on our way to driving that number down. And of course, everybody is working on net zero cements. There are a couple of plants in Scandinavia being built. Bill Gates is trying to secretly work on this energy source. The biggest problem, of course, for cement is in order to create the clinker, which becomes the cement, you have to punch in a lot of heat that is only possible with fossil fuels right now, coal, really. And so the idea is to reduce the emissions from calcination, all terms you probably heard about, but that's a part of the production process, and drive that down to zero. And so people are working on it, and there's a plan. But we have to know that every material has embodied carbon emissions from their life of the use of the material. If you look at steel, the mining of the iron ore, the raw materials, to the production in the electric arc furnace, which is more efficient than the basic oxygen furnace, to transportation of the members, to its use, and then at the end of life, every one of these stages has some impact on our environment in terms of the emissions. And for steel, much of it happens at the end of life because it gets recycled back, so we can reduce the amount of emissions of the material by looking at the full life of it. Wood, however, is a different metric. A lot of the impacts of wood happens at the extraction phase, because think about how much of a large tree actually becomes a wood product, right? They have to, you're not using the bark, you're not using the leaves, the branches, you're not using the roots, you're not using the soil that is also absorbing the carbon in our forest. All of that is logging residue and ladder that is either burned as biomass, goes up in the atmosphere immediately, or it's burned on site. And then obviously there's any production of materials has emissions for the creation of a wood product. And at the end of life, what happens to that material? Is it recycled, or is it in a landfill? And then I'll get into the details of impacts of concrete. But again, for concrete, the cement manufacturing is the primary driver of the carbon footprint. That is the fossil fuel use and the chemical reaction called calcination that releases carbon. Concrete itself is probably only 20-30% of that whole assembly's carbon footprint, primarily because you always use local materials, as I said, when you are getting sand and aggregate, which is everywhere around the world. You're not transporting it that far. There's a benefit to the use of concrete. I'll talk about that later for the use phase, unlike steel or wood. And there is carbon sequestration that happens with concrete as well. And so that is, take a life cycle perspective when you're looking at carbon and also other environmental impacts when you are considering materials, any materials. I'll take a break right here if there are any questions that might have come up. Anything? Nothing. Yeah.
Nope,
okay.
There's nothing. I'm just confirming there was nothing so far.
Okay. Thanks, Grace. Yeah, so if we take a life cycle perspective, we can look at the product or the material in each stage of its life and see how we can apply strategies to reduce the carbon or other environmental impacts in these stages. And so I'll just be going through this. You don't have to read this. Material acquisition and production, construction, use phase, and the end of life. All for concrete has an opportunity for the designer and the engineer to reduce its carbon footprint. And so I use this term just many times in the beginning of this presentation, embodied carbon. Really, embodied carbon happens throughout every stage of the life of a product, from material acquisition to production, and the construction, use, and end of life. For the use phase, it's the replacement of material think about your roof shingles, think about paint. Those are products that have a life that has to be replaced. So that is a part of the embodied carbon. But much of the discussion in the design world today, and also legislative action that I mentioned before, is about embodied carbon upfront, initial or upfront embodied carbon. And that is primarily focused on material acquisition and production. And so one of the main strategies, the most important strategies, to understand and set targets for your project. That is to say, setting a carbon budget by understanding the project's carbon emissions and making sure that you work with and communicate those targets to the whole team, including the producers of concrete or other materials, for instance. And many times we know, even from my work, the architect or the developer is so far removed from the production of the material. The concrete contractor, maybe not even talking to them, to the general contractor. And so having the whole team understand the goal is very important. And there are tools out there right now that we can use from a design standpoint that, you know, some are free. Athena is free. Tally can be integrated into your Revit. One-Click is also more popular in Europe, but getting popular in the US here. EC3 is also a great tool that makes comparisons. It's not exactly a life cycle assessment tool. It just takes the data and makes comparisons. And you can use this little equation I put on the bottom by saying, look at all the mixes in your project and combine them to be a sum so that you can use that as your footprint. And part of the important way to do this is to make sure you the project has disclosure of the various materials carbon footprint. And right now we have this disclosure that we regularly work with on our food products, right? We see ingredients, fat, carbohydrates, and we just take that for granted. You know, that's not even, this is really only a very recent phenomenon. I think 1990 is when it was made into law that food products needed to show their nutrition facts. And so the disclosure of environmental impacts already is happening in our rating systems that we see, and using these type of metrics to quantify. It's not just a, oh, I have 70% recycled content type of conversation, or it's within 500 miles or 100 miles. Who cares how many miles? It doesn't really matter when you look at how much all of the environmental impacts combined will make the item high or low in its carbon footprint. So it's quantifiable. And these type of disclosures happen with environmental product declarations. That's EPDs for short. I'm sure you've been hearing that, lots of that. The concrete industry, we started 7 years ago to help create the rules, the product category rules, and to create our industry benchmarks, as well as over 36,000 product-specific EPDs, so that we can measure, track, and make sure we understand how to reduce the carbon footprint, as well as other environmental impacts of our product. And so that's the first big step, is to make sure you understand and communicate the targets. The next thing is something that we do, we should be doing intuitively, which is optimizing the design. So at the production stage, at the design stage, even before the production, the design stage, we want to optimize it. That means using less concrete or cement. Actually, the industry doesn't want me to say use less. They want to say optimize because it sounds so much better. But essentially, you want to use this really important material where you need it, right? If you can use a higher strength concrete to reduce some of the intermediate columns on a concrete frame project, then you've reduced some of it, even though you used higher cement content. Or if you have, in say, a larger building, you have concrete that is on a column that's exposed and you want to see it for aesthetics, should you reduce the column's diameter at the base, at the upper floors versus the base where you need the same strength? Is it aesthetically required so that you don't have to have the same volume that you need? Same thing with exposed concrete. Making sure concrete's exposed. Concrete's a beautiful building material, and materials to finish a concrete building has a high carbon footprint. Expose it and have less material in the building. And with regards to exposure, let's say you're exposed to freeze thaw, making sure your specifications don't call for air entrainment in your non-exposed to freeze thaw mixes, such as the mixes on the interior. So making sure your specifications are correct. I'll talk about that a little bit later, but just thinking about the chemistry of how concrete is done. If you have air entrainment, that means you've got these little bubbles inside the concrete that the material has to span, which means it needs a little more strength in the cement. And if you didn't need to do that, you can reduce the amount of cement that's required. So little steps that will help in the design and optimizing the volumes. Of course, we've all known for many years about SCM, supplementary cementitious material. SCMs are the industrial byproducts, and pretty much all concrete in the United States already uses SCMs, because in the old days, we used to call it, oh, let's recycle some content and make us feel good about it by recycling stuff that is from other industries. But we really know now that SCMs improve the performance of concrete, maybe not in early strength, but in ultimate strength and in workability of the material. And so it is the easiest solution we have right now, today. Tomorrow, you can just use this to drive down the concrete carbon footprint with any producer by simply adding this material. I say simply, there's actually a shortage in many parts of the United States, including here in the Pacific Northwest. One of the important things that the cement industry is doing is bringing blended cements into the U.S. market. Blended cements have been used for 30 years in Europe, 10 years in Canada, somehow very slow to come into the U.S. market. It's a little bit complicated, but it has to do with our history of separation of our cement industry with the concrete industry. The concrete guys didn't trust the cement guys and didn't want them to give them, cement that was cut with other materials. And so they wanted to blend the cement with SCMs or other products on themselves at the concrete plant. So right now, Portland limestone cement is widely used here in, at least in the Seattle market, Oregon, and just starting out in California, some in the Northeast as well. It is an easy way just to immediately get to 9 to 10% reduction in your carbon footprint without changing anything else that you have to do with the concrete, simply by using Portland limestone cement. The problem, of course, right now is many specifiers, architects, engineers do not have type 1L ISIP, these type of hydraulic cements, C595 and ASTM C1157 allowed in their specification. So we have to make sure it is permitted on the specifications. And there are tons of examples in British Columbia that is using Portland limestone cement. And so these projects all have reduced the carbon footprint of their projects, and essentially the three major producers here in at least in the Seattle area, that's all they're using really right now. So you could be getting Portland limestone cement and reducing the carbon footprint of your next project without even knowing it. But making sure that you have it permitted in your specifications is important. Another item in the production stage is enhancing the carbon capture. Carbon capture, utilization, and storage is the big term for lots of climate activists right now. That's the future of all materials, and that's how we're going to solve the climate problem. I've been hearing that from people for the last decade. In fact, I was hearing that from people from Weyerhaeuser, where I used to work, over 20 years ago. And so the idea is that we want to be able to use carbon the same way you use carbon in your soda pop, Coca-Cola, Pepsi. And that is to either inject it or use that carbon dioxide into the creation of new aggregates, in fact. And so this carbon mineralization already is happening right now to the concrete that folks, and there's a number of different pilot projects. San Francisco Airport used this aggregate. Many projects in California already have this carbon injection process. They're also injecting carbon into fly ash. They're injecting carbon into precast concrete and block material. So it's already happening now. And we're at the earliest stages, but we want to encourage this by allowing this type of innovation to happen. And here's a project in Atlanta that already, sequesters 680 metric tons of CO2 in its use in concrete. All right. So any questions on some of those innovations at the embodied carbon extraction and production phase that coincide, align with what architects and engineers can do? Anything? No? Okay.
I'm not seeing anything. Go ahead.
Okay. Anybody there? All right. So at the construction stage, there are also things that can be done to help reduce the carbon footprint of material. We know, obviously, concrete is a versatile product. At the same plant, you're getting different mixes with high strength, flowable concrete, something that you can pump a long distance, something that has the finish like, this church that Tadeo Ando did, type of things. Everything can happen in one plant just on the type of mix that's specified. And one of the most important things, innovations that we always have been using, but we haven't thought about it as a carbon reduction strategy, is admixtures. If you think about something like high range water reducing admixtures, it's so effective at reducing the amount of water content. Remember, concrete strength comes from the water cement ratio. You have to make sure that is constant. And when you reduce the amount of water, you're reducing the amount of cement. And that way, to keeping it at the same strength, you can reduce the carbon footprint of any mix simply by 12% by making sure that you're using a high range water reducing admixture in a project. And so admixtures are very important to reducing carbon footprint. But more importantly, we already know that technology is not the challenge. It's actually scheduling. When we have to pull forms from a PT deck, for instance, we know that we have to have a lot of cement content. You cannot have a lot of SCMs in that because, in 3 to 5 days, the contractor wants to pull forms. Essentially, our concrete is designed for contractors, not really for the project. We can build the same things that the Romans did 1,000 years ago, 1,000 years, or more than 1,000 years, 2,000 years ago. But we don't have the luxury that they did of time. We want stuff, our owners and contractors want things done very quickly because time is money. And so when you have to have high early strength, you need a lot of cement. If you had mat slabs, footings, shear walls, projects where you don't care about high early strength and only want to measure later strength, 56 days, 90 days, for instance, you could put in a lot more SCMs because you don't care. And so you want to balance the mixes with the different type of performance requirements that you needed. So, here you can see a project, a baseline that has all the mixes, whether it's for 1,000 psi or 10,000 psi to 8,000 psi. This is obviously for a very large building. You can compare it to the baseline by driving down those mixes where you need to get to a lower carbon footprint. This happened essentially in the Helen Summers building in Olympia. This was a Cellum project. The concrete was provided by Cal Portland. And they basically looked at the various mixes and make sure they optimize the SCM content where they needed to. We learned as the designers that 28-day strength is how you look at concrete. But the reality is you want to look at concrete strength when you need it. And so this project was able to make reduce the embodied carbon concrete of the concrete by 31%. Obviously, there are also innovations. I kind of use the term lightly, innovations, but innovations such as insulating concrete forms, SCC, tilt up, SCC for really large buildings. Essentially, that's how we build high rise. We've got to be able to pump it and flow it very high up. And so things like tilt up, we already have great examples here on small scale projects even. It doesn't have to be the Walmarts and the Home Depots. It can be like the St. Ignatius Chapel that we have. This is a tilt up project and can go and went up very quickly. And the speed of construction obviously saves time, money, and the amount of carbon that is being used in the construction process. This Pierce County Readiness Center is a great example of using ICFs, insulating concrete forms, and it's built for the type of hazards that we will see here in the Pacific Northwest when the big one hits or other hazards. And so another ICF project that's a passive house in New York, the Bluestone organization essentially uses ICFs solely, and they do affordable housing in New York City. Okay, and so the production and construction phase, we've heard there are opportunities to reduce your carbon footprint. Product use, most materials have nothing to do with product use except when you replace the material. And when you look at concrete as a material, we know it lasts a long time. So we want to use material where we need it for its strength and durability. But concrete also has, because of its opportunities to last a long time, we see that the first graph that we saw where the looming deadline of 2050 from the Paris Accords doesn't think about what happens to the project after that. We know these buildings, especially ones that will be built in concrete, will last another 70 years, for instance. Um, and in that time, we'll know that the embodied carbon will remain the same pretty much with some replacement of materials. But for durable material like concrete, it'll essentially be only a quarter of the overall carbon of the project. In a 60-year forecast, we'll see that in fact the operational impacts, that is the heating, cooling, electrical use, will overshadow the embodied carbon. We have to plan for that. If you think about having more embodied carbon in terms of insulation in your project, there's obviously a break-even point. But if you have more insulation, you might save more in the operations in the long run. So having more initially better windows, triple glazed windows, for instance, all of that costs more in terms of embodied carbon, cost of carbon, but benefits in the long run. And so we have to understand that the decisions at the initial embodied carbon stage, production and extraction stage, affects the operations phase as well. We know the benefits of thermal mass. Those of you who worked in, high mass buildings such as rammed earth or concrete know that there is benefits of moderating this thermal lag and dampening the peak demand and of energy, allowing not only cost savings from reduction of HVAC equipment, but also more comfort and reduced carbon in operations phase. This is the strategy that the schools in Kentucky, we can learn a lot from Kentucky because we don't do this right now in Washington State. The net zero schools, there are dozens and dozens of net zero schools in Kentucky, and they were the first ones to do this. They essentially get the paycheck of one school teacher every month from the utilities by having a building that is net zero. Richards Elementary School just happens to be the first one. And when I was on the Code Council, we talked about how much we can put into the walls, the envelope of the building to make the building even more efficient before. But there is a point of diminishing return for our buildings. We can't all make buildings that are so, so super insulated like Passive House. We should, but right now it becomes a cost prohibitive as well as something that is technically some folks are still only getting to understand. But what we can do is reduce the amount of heat island effect that happens that encroaches onto the building. So a lot of the hotter climates, for instance, we know that the heat island effect of our asphalt pavements and our parking lots and all of that can drive the heat up around the building that has to be cooled, in fact. And so it can be 3 degrees warmer in residential zones and up to 7 degrees warmer in commercial higher density zones. And so there's opportunity to reduce the amount of heating and cooling by using a high albedo material like concrete, meaning lighter in color. Same thing for the amount of lighting that you need to, when you think about a parking structure, to light a parking structure. So again, energy use in the operational use phase. I'll take a break right now. Any questions on that so far?
Hey, Tien. Yeah, I'm going to relay some things that are in the chat. And I also wanted to give you sort of a heads up on the time and do a time check.
Yep.
I know we started late, but we have about 5 minutes left of what the official session time is. And I know we did start late and everything. So I don't know how close you are to the very end of your...
I'm at the end of life. See that? End of life.
Okay, so I'm going to relay a couple of things. One is Just wanted to let you know there's a representative here from the Built Green certification program, and she said that the 2021 checklist includes upfront carbon emissions disclosure and calculation credits for residential projects. So that's a residential checklist. Didn't know if you were aware of that. And then there is a question from regarding an earlier part of your presentation, and I'll just read it. It's from Cindy, and she says, "Is concrete with bubbles more wasteful than no bubbles? Recommendation for someone building a structure to access the information you're giving to make the right choice around optimal cement with sequestration abilities."
Well, concrete with bubbles and without bubbles is not necessarily having to do with sequestration. So two separate topics. Concrete with bubbles, meaning air entrainment, should just be used for exposed concrete outside. And it will, using the EPDs, give you quantifiable differences in the concrete mix. So you basically have to work with the producer on that one. But all of these strategies that combined should add up. It's all additive. So you can help yourself out by choosing many of these strategies. I'll finish up and then see if that answers the person's questions. Okay. End of life. So end of life is important because concrete is one of the most recycled material out there. Probably less than steel, but it is being recycled because C&D waste is very expensive. Nobody wants to pay for concrete to be dumped in a landfill. So much of it, especially in Washington State, is already crushed and used as roadbed. And recycled concrete aggregate is in our laws to be used in fresh new concrete. So the embodied carbon you used to create concrete in the first place can just be maintained by putting it into fresh concrete. Not all fresh concrete, just a little bit. And it would certainly help to sequester, to use that term, to help, even if it's like up to 30% of recycled concrete aggregate, wouldn't change the concrete mix significantly. Obviously, the chemistry has to be known by the producer, but obviously that is a way. But concrete is already a sequester of carbon. It's estimated that 20% of the emitted carbon dioxide is being sequestered by concrete throughout its life. It's called carbonation. It's something that we don't like. We try to solve this thing, but we see carbonation that happens to concrete. And in fact, the IPCC has directly addressed this by putting that into the most recent assessment to understand the reabsorption of the carbon that was emitted by concrete is being sequestered back in. Obviously, the most sustainable building, the most carbon-free building is one that you don't have to build twice. And here's an example, obviously, of the benefit of keeping a building that these guys had in Mexico Beach during Hurricane Michael in Florida in 2018. Saw that in the news. And right now, we are working with a number of habitat projects around the country to rebuild from a lot of wildfires that you saw and elsewhere from tornado damage. In fact, I'm going next week to Paradise, California. If you remember, Paradise, California was totally devastated by a wildfire. We are rebuilding that with a habitat using a material that won't burn in the future. So to end my talk, look at the whole life cycle when you consider a building, environmental impact, and there are many proven results. Sorry I didn't show any residential projects, but certainly there are many projects that use concrete, even on a residential scale, that can reduce this carbon footprint when you take the whole life into consideration. Okay, ready for more questions. I hope that one answered the other person's question.
I am not seeing questions. Sometimes people are typing as they're thinking. So I am not seeing anything right now. Anything else from previous? But I have a question, since I mentioned this when we were backstage before we went on here, and I know as a practitioner who is working in the residential world and small scale on homes, and I think a lot of our audience is also in that same boat at this conference. And what would you say? Well, so it's hard to figure out which strategies, green building strategies, we're gonna take. And I know that I mentioned that I had a client recently say, okay, and we're gonna use low carbon concrete, and I went, right. And first thing in my mind was, how am I going to get that to happen on such a small scale? So my
Right.
question, I guess, is, are there options for things like that in this area, in the Seattle area, on that small of a scale? And with that, the second follow-up question would be, what would you say on small residential scale would be your, like, I don't know, first three things to do?
I think the biggest thing that can happen is to one, communicate the goals by saying, what does that mean to your client? What does lower carbon concrete mean? If it means that they want you to prove it, and that means you need to make sure that the concrete you're getting, whatever that mix is, has an EPD, because that's the only way you can prove it, right? You can also say something like, making the other step you need to have is to make sure your specs are permissive, making sure you have allowable blended cements, making sure your specs don't limit SCM content, water cement ratio, cement content, higher or lower, upper or lower limits, making sure those prescriptive words, language in the specification is gone, because then you're essentially tying the hands of the producer to give you what you want. And so communicate specifications, and using the communication tool, the tools that you can use is already available for you for free. For instance, EC3 was created right here in our backyard with the folks from Carbon Leadership Forum, Skanska, and Stacy Smedley is, a superstar here. She's leading that charge. That essentially is a free product that you can go in and get that mix number from your producer and say, oh, compare that to their benchmark in the EC3 tool. It's not the same as the NRMCA benchmark, but we don't need to argue about the differences. And that benchmark will already tell you that number, how much it's reduced. You can say, oh, well, you can ask the producer something as simple as how much SCM content was used in that mix. And that already tells you how much reduction by taking out the cement and putting in an alternative. And that is a very basic layman's, I guess, metric, without getting into the global, kilograms of carbon dioxide equivalent per, yard of concrete in EPDs. That was my three. How's that?
Great. All right, we have some questions here, so I'm just going to read them off. Sage is asking, have you considered Fazwal in your habitat/residential Habitat for Humanity? I'm taking it to mean /residential endeavors.
I don't know fast wall. Is fast wall the one that is got the insulation you poured and it's in the ribs, or is it what? I don't know what it is.
No, I believe if Sage, would you like to come up on stage and describe your question?
Oh, come up on stage! Wow,
We can do that. I don't
what?
know.
Get in my face! Hey, you! Like,
I don't want to have to break up a fist fight, a virtual fist fight.
I think we have to invite him up somehow, but
Yeah,
oh,
I don't know if we can invite him actually. I think
I mean, I could
there
look
he
up.
is.
There he
There he
I
is.
could look up fast wall if somebody wants.
Hey there. All right. Well, thanks for the invitation. I'm just, when you showed that photo of, and by the way, thanks for your presentation. When you showed that photo of the foam and your text about habitat, Fazwal is a locally produced product, which is recycled pallets that have been chipped, and it's a block. So it's about a 2 foot by 1 foot by 8 inch block. And then they run that through a slurry of minerals and cement and make this block that's somewhere between 26 and 30 pounds in it material. So for instance, for a habitat project, that would be something that would be pretty easy to train people in slinging the blocks around.
Right. I'm not familiar with the product.
Oh, Helen just put
Thank you.
a link in there to the product. So definitely worth checking
Yeah.
out, Tien.
Yeah. Thanks very much.
You're welcome.
Okay, great.
You get to sign me out of here. You got to boot me off, or do I?
Yeah, you can just turn your mic and cam off.
There we go.
There we go. All right. Thanks, Sage. And we have another question from Kimber asking, is injecting CO2 in concrete readily available to use now?
I would say it's if you are in the Washington market, somehow it is not available here yet. It's available in Northern California, some other parts of the United States. Basically the producer has to sign an agreement and have a piece of equipment be put on the production plant and have this regular shipment of carbon dioxide diverted from the Coca-Cola plant into the concrete plant and then injected. So it's a licensing thing. It's available right now in different places in the United States. It's not available right here, unfortunately. They are working on that. Part of it is a lot of it has to do with testing. So much of concrete is tested for the different constituent materials. So it has to work with the cement and the aggregate that is here, and so to meet the specific performance. So it's not that it can't be here. It's just it hasn't happened yet.
Great. With that, we have one more question and 1 minute left. So
I was going to suggest that we could have Tien go. Forget what it's called. There's a table down in the bottom right, and people could meet him there and ask him more questions too. So we could just do that.
I'll go to the table later.
Okay.
yeah, do you want to go ahead and answer this one question?
Sure.
And hopefully we won't get in too much trouble for running a little over. I'll just read it. A few years ago, MIT students were researching recycled plastic in concrete. Do you know anything about that and whether there is any traction or real viability to it?
I get calls a couple of times a year about people want to throw things in concrete. I'm all for it. Every time some foundry has some glass in their backyard, they want me to throw it in concrete. Right now, you won't believe how much concrete is being used, and the concrete plant has silos that gets permitted to be put in there, and it takes a lot of work to put in a new silo of stuff, of junk or a little pile someplace to use in concrete, it it's asking the producer a lot because they have this operation that is nonstop, and you're like, hey, can I throw some plastic into your concrete that we scooped up from the Texas garbage patch in the middle of the ocean? So having said that, I actually work with MIT on a number of projects, and I have not heard of this particular one, but somebody did, not from MIT, talk about scooping up plastic from the garbage patch in the ocean and taking that plastic and putting it into concrete. And when I looked into it, it turns out it was non-structural. So I'm like, well, I don't care about concrete that's non-structural. You can do that anywhere. It doesn't require anything for you to use concrete that is non-structural. You don't need a permit to do whatever you want with that concrete. It's the structural ones that I worry about. So no, I have not heard specifically on MIT plastic, but there are lots of innovations I'm sure I have not heard about. And there's stuff, like hempcrete is been around for 10 years. And apparently it's taking off now because hemp is a big thing. So I don't know about that particular one.
Well, on that note, we are going to close out this session. Thank you, Tien. And this was really enlightening. I haven't thought about this much of concrete in a long time, so it's good for me. If you have a few minutes available, as Wendy mentioned, we'll go off the stage and we'll plant ourselves in the lower right corner table.
Yes.
So if folks have more questions, can find Tien there. All right, thanks.
Thanks very much.